Have you ever been scrolling a web application when it suddenly stutters and completely locks up? That freeze is a symptom of a thread block. Today, we are going to bypass the high-level JavaScript frameworks. Instead, we are going to autopsy the C++ browser engine internals to see exactly how code is converted into physical pixels on a screen. The core architectural constraint of the web is the main thread. HTML parsing, style sheet calculations, and JavaScript execution are all processed on the exact same synchronous execution context. Because they share this single lane, executing a heavy synchronous JavaScript task physically blocks the browser engine from calculating layouts and updating pixels. Achieving professional web performance requires abandoning the idea of simply writing faster code. You have to master the physics of the main thread. The critical rendering path begins when the browser receives a stream of raw HTML bytes. It converts those bytes into readable characters, parses them into tokens, and builds a branching data structure. These nodes are linked together to create the Document Object Model, or DOM. This diagram shows the standard top-down hierarchy of that model. It traverses from the document root down through the HTML, body, and specific nested tags like headings and paragraphs. Simultaneously, the browser parses incoming style sheets to construct a parallel structure known as the CSS object model. These two structures then merge to form the render tree. During this step, the engine optimizes for memory by stripping out any nodes with a display none property. If it isn't going to be visible, it doesn't make it into the render tree. Next is the layout phase, commonly called reflow. The browser engine calculates the precise X and Y geometric coordinates for every node, creating a wireframe blueprint of the page. Then comes the paint phase, or repaint, where those geometric blueprints are finally filled with actual pixel data, colors, borders, and text on the screen. There is a massive discrepancy in CPU cost between these two phases. Altering the structure or geometry of an element during reflow forces the engine to recalculate the positions of all surrounding elements. Simply changing a background color during repaint is significantly cheaper. This brings us to layout thrashing. If your JavaScript repeatedly forces synchronous reflows, say by reading an element's width and immediately changing it in a loop, the paint phase is completely stalled. The UI locks up. Building the render tree gets pixels on the screen, but at this stage, the user interface is completely static. To enable interactivity, the engine must initialize the event flow. Every single browser event is a discrete, memory-allocated object that physically travels through the entire DOM structure. This journey happens in 3 phases. Phase 1 is capturing. The event object trickles downward from the window root, passing through every ancestor node in sequence. Phase 2 is the target phase. The event object makes impact with the specific UI node the user interacted with, triggering any listeners attached directly to it. Finally, Phase 3 is bubbling. The event object reverses course, traveling back up the exact same ancestor chain to the root. By default, the standard addEventListener method is hard-coded to listen only during this upward bubbling phase. If you need a listener to intercept the event during its downward journey, you must explicitly pass the captureTrue parameter into the method. This predictable spatial traversal path gives us intricate control over user interaction, but it also creates a significant system vulnerability when building at scale. Consider a complex, dynamically generated UI list containing 10,000 data rows. A common mistake is iterating through that list and attaching an individual event listener function to every single one of those child nodes. This creates an O of n memory footprint. Your RAM usage scales linearly and aggressively with the size of the DOM. This pattern traps you in a web of circular references between isolated DOM nodes and JavaScript functions. If you delete those rows from the UI without explicitly removing the listeners, the memory remains occupied. The browser's internal garbage collector goes into extreme overdrive, desperately trying to untangle and clean up these detached nodes. Because the collector runs on the main thread, this monopolizes the CPU and causes the UI to freeze. Treating events as localized actions attached to individual elements creates a performance bottleneck that becomes unmanageable as the UI grows. The architectural solution is Event Delegation. We completely remove those 10,000 individual child listeners. Instead, we exploit the bubbling phase. We place one robust listener on the common ancestor node to catch events as they naturally rise up the tree. This single-parent listener can manage an infinite number of dynamically generated child nodes without requiring any additional memory allocation. To use delegation properly, you have to navigate a notorious interview trap, understanding the strict difference between event target and event current target. Event target is the raw, deeply nested element that was physically clicked by the user, like an inner span or an icon. Event current target is the ancestor element where you explicitly attached the listener. Event delegation restructures the interaction model, converting an O of n memory requirement into an O of 1 constant time operation. With events effectively managed, we move from passively listening to actively controlling, altering, and canceling them mid-flight. First is event.preventDefault. This stops native behaviors, like a form submitting. Crucially, it does not stop the event object from bubbling up the tree. Second is event.stopPropagation. This command halts physical traversal entirely, shattering the event object in the capture or bubble phase. Third is event.stopImmediatePropagation. This stops the traversal up the tree, and it instantly deactivates any other sibling listeners attached to that exact same DOM element. Blindly calling stop propagation is considered a significant code smell in modern single-page applications. Modern tools, like React's synthetic event system and enterprise analytics trackers, rely on global listeners attached at the document root to function. Stopping propagation inside a child component completely kills these system-wide functions. Event cancellation tools are surgical instruments. They require a holistic understanding of the entire application's architecture, not just localized UI fixes. We've tracked the life cycle of the web page, from parsing raw HTML bytes to constructing the final render tree. We've seen how the engine transitions a static geometric blueprint into a live interactive UI via the three-phase event flow. We established the absolute necessity of maintaining an O of 1 memory footprint using event delegation to prevent garbage collection thrashing. And we've seen the precision required when utilizing event cancellation to avoid breaking global listener states. Mastering these low-level browser internals separates casual framework consumers from the true systems engineers capable of dominating enterprise architecture interviews.